Hi, welcome to this last video series of this course. In this video series, I want to give a very short video where I show Bayesian statistics. Bayesian statistics are an alternative to frequentist statistics which we have used so far, which underlies, for example, the p-test and the ANOVA and basically everything we did so far. Bayesian statistics offers an alternative, and I feel like I have to talk about this because I teach using JASP. JASP is actually a software that's designed to do Bayesian analysis as well. So I want to explain that as well. It's a term that comes by sometimes, and I think it's good to know a bit what it means and what it can do. Now, I'm not going to go into detail. Bayesian statistics is actually pretty complicated. So I'm not going to go into the mathematical detail behind anything or really explain how you do a Bayesian analysis. I just want to expose you, give you an idea about what this is all about. So earlier in the course, I talked about different ways in which you can interpret the concept of probability. You might think that probability is something that we all agree on what it means, but this is actually not the case. There are two main ways in which you can interpret probability. The classical or the frequentist way, which we have been using so far, and the alternative is the Bayesian way. So in classical frequentist statistics, the way that we interpret a probability, let's say the probability is 0.20 that something happens, is a long-term frequency of something happening. That means that if we say a probability is 0.01, this means that in repeated samples, if we do something over and over and over again, in the long run, you would expect to find something 1% of the time. Right? So P equals 0.01 literally means if you would do the same experiment in new samples over and over and over and over and over again, and suppose that there is actually no effect, the null hypothesis is true, then the 1% of the time we're going to find a statistic that is as extreme as the one that we found in our data. That's the interpretation of the p-value. And this relies on this frequentist view of probability, a long-run frequency. If you would keep repeating something over and over and over and over again, we would find something a certain proportion of the time. Now, importantly, in frequentist statistic, we assume that there is one real reality, and we can draw new samples from that reality. Let's say, for example, we're interested in an effect, a relationship, a correlation between, let's say, happiness and loneliness. Yeah. And maybe there is no correlation. Maybe the true correlation is actually zero. Right. It's the null hypothesis is true. Then any sample we take is actually a draw from the null hypothesis. And if we do this over and over and over and over and over again, we're going to find a significant effect exactly p amount of times. That's the interpretation of the p-value. Now, importantly, in the frequentist statistics setting, the null hypothesis is either true or not. There is some underlying ground truth, right? So there's a true correlation in the world, in the population. If we would measure everybody, the entire world, for example, in all possible settings, we would find that exact true correlation. It is either true or it is not. So the null hypothesis is either false or it's not. It's not sometimes false and sometimes not false. It is always false or it is always not false. Right? And if it is false, then we find a significant effect with a probability equal to our power. If it is not false, so if the null hypothesis is true, it means there is no real effect. We find a significant effect equal to our alpha level, right, which we determine. The big difference in Bayesian statistics is that they view probability in a very different way. They don't talk about long-run frequency. They don't find this interesting. They don't care. They're like, okay, I have one data set. Yeah, I get one data from my data. I care about this data. I don't care about potential other samples that I could take at long-run frequencies, and I find it weird. And they see probability as a degree of belief. Importantly, a subjective degree of belief. And this is a core difference. So when a Bayesian says, and then Bayesian can say this is a probability that the null hypothesis is true, equals 0.80, it means that they're 80% convinced that the null hypothesis is true. So it means they don't know the null hypothesis is true or not, but they believe for 80% certainty that the null hypothesis is true. And that's the idea. Now, it's subjective because someone else might have a different degree of belief. And the same data might lead to a different degree of belief in me compared to you. And this depends also on what you believed before you saw the data. Right, so let's say, for example, let's say the psi experiments from them. And let's say I don't believe in clairvoyance. I find it very, very hard to believe. I have never seen evidence for it. I don't think that it's real. Right? If the data tells me, I'll be convinced. But a priori, before seeing any data, I have a very hard time believing that's real. That means that you would have to present a lot of really compelling data to me to make me convinced that it's actually real. Where someone else that actually does believe in clairvoyance might say, okay, I actually already had a prior idea that this might be real. And that means that that person might require less data to be convinced that clairvoyance is real. Right, so to get the same subjective degree of belief that clairvoyance is real, let's say 80%, I would probably require more data because I have a different subjective degree of belief than maybe someone else. That idea, talking about subjective degree of belief, is just something that you cannot even do in this frequentist framework. It doesn't make sense because we're talking about repeated samples and the null hypothesis either is true or it is not. So this is this comic here on the left from XKCD. Did the sun just explode? And what happens here is there is a machine. This machine detects if the sun exploded. It's a weird machine. So it will be honest, it will say yes, the sun exploded, if the sun exploded. But if the sun did not explode, it will actually roll 2 dice, and if they both come up 6, it will lie to us. Now getting 2 dice to throw, getting 2 6s is a probability of 1 in 36. But that's actually pretty hard to get in when you throw 2 dice. It's less than 5% of the time. So what happens here? We ask, okay, has the sun gone supernova? Did the sun explode? And the machine says, yes, it exploded. Alright, so this is an event that would happen less than 5% of the times if the null hypothesis is true, if the sun actually did not explode, right? A frequentist would say, okay, we accept that we reject the null hypothesis, because in this case, this data was unlikely to happen if the null hypothesis is true. Namely, the p-value is 1 over 36 is 0.027, which is less than our alpha level, so we conclude that probably the sun exploded because we can reject the null hypothesis. Now what does the Bayesian statistic say? I bet you $50 it hasn't, because the Bayesian statistic has like a stronger prior belief, and it is like, okay, this is a very unreasonable thing to say. We probably need much more evidence to support this. Now, Bayesian statistics are inspired by the work of Reverend Thomas Bayes, and this is a reverend that lived in the between 1701 and 1761. Now, this is a very famous picture of Thomas Bayes, except that we don't know if this is actually Thomas Bayes. This is the only suspected image of Thomas Bayes. It's the image you see appear a lot. Every time people refer to Bayes, they'll use this image, but there is a certain degree of belief that this might actually not be Thomas Bayes, but overall we think this is a picture of Thomas Bayes. Now, Thomas Bayes developed the idea of Bayesian statistics. Bayesians view probability as a degree of belief. So because they see probability as a degree of belief, they can suddenly talk about things that frequentist statisticians cannot talk about. They can talk about the probability of a hypothesis being true. A frequentist or someone doing frequentist statistics cannot talk about this, Because the hypothesis is either true or it is not true. If it is true, probability is 1. If it's not true, probability is 0. It doesn't make sense to talk about probability of something that is either true or not, that is actually, as we call it, fixed and not random. But the Bayesian can say, no, I have a degree of belief that my hypothesis is true. This degree of belief is initially subjective and it can differ from person to person. Right? So my prior beliefs might lead to a different posterior beliefs, as we call it, where prior means before we see data, posterior means after we see data, and someone else. Now this is a big problem. Yeah. It depends on who you ask, actually, because some will say this is the strongest thing about Bayesian statistics, that you can actually quantify subjective belief. Others will say huge issue, because it means that my conclusion might be different from yours given the same data. Not something we like in academia. We like just a fixed p-value, right? The data is this, we have objective tools, and then we get some conclusion. This is a reason why Bayesian statistics is hard for some people. But the core focus in Bayesian statistics lies in that there is actually a way to objectively update your prior beliefs to posterior beliefs. And this is the main thing that we do now when we do Bayesian statistics. So we have prior beliefs. Our prior probability that something is true. So let's say my prior belief that clairvoyance is true is 0.01, for example, like 1%. Right, sure, if someone gives me really compelling data, sure, but I'm a skeptic. And after I see data, I update my prior beliefs to posterior beliefs. Posterior beliefs are, how much do I believe in something now after I saw the data, right? Maybe I read Bem's work, it's not bad, right? He did some okay research, it's and maybe I update my prior beliefs, but it's definitely not like 50% or anything. Maybe it's like, sure, 5 times higher, 5% rather than 1%, right? But still very, very, very low. Both prior beliefs and posterior beliefs are in a way subjective there, depending on me. But the way that you can go from prior beliefs to posterior beliefs, is updating of beliefs. That is something we can objectively do. And this is the big thing, actually, that what Bayesian statistics is all about, really. We can do that using a formula called Bayes' theorem. And Bayes' theorem dictates how a rational, logical thinking person, and with rational, logical thinking person, we always mean like a person that actually adheres to the laws of probability and that will make decisions based on like rational probabilities. Our rational, logical thinking person should update their prior belief, degree of belief, to posterior belief, degree of belief. Bayes' theorem. I want to show this, what this looks like. So suppose I have a data set, and I'll turn this data D, this stands for data, and I have two competing hypotheses. A null hypothesis, there is no effect, right? So beta 0 equals 0, or beta, some parameter, doesn't matter what. An alternative hypothesis, there is an effect, so beta not 0. We've seen this so far, before, right? It's not different than what we do in null hypothesis significance testing. We have a hypothesis that there is no effect versus a hypothesis that there is an effect. The likelihood of the data describes the probability of observing a certain dataset given an hypothesis. For example, 8-0. This is a very important term in statistics. It's a distribution of your data, meaning your probability distribution of your data, or how likely is it that you find a certain pattern in your data, given that an hypothesis is true. So you remember, this symbol here stands for probability. This symbol in the middle stands for given that. So this stands for the probability of seeing a certain data set, given that our null hypothesis is true. So we call the likelihood of the data. And this is exactly what the p-value is based on. The p-value is calculated from this likelihood function, as we call it. Right? That is pretty much the p-value. Right? How likely is it to observe this data, or more extreme cases, given that a null hypothesis is true? Right? We can define this right, using our our model, or using our distributions, and we can get a p-value out there. So this is what we did so far. In Bayesian statistics, Bayesians can actually talk about probabilities of the hypotheses themselves. So the Bayesian is not interested in the probability of the data given the hypothesis. But the Bayesian doesn't care about that. Right? Why is it important to look at how likely it was that our data occurred under a certain hypothesis? The Bayesian doesn't care about this. The Bayesian is actually interested in flipping these things around. The data is what we see. The data is fixed. Why would we model the probability or the likelihood of a data set? It's not even interesting. We see a data set, that's what we observe. We don't have other data. Well, why would we look at, under potential new samples, we would get a similar data set, and maybe we would find another t-value that would be about as extreme? Why? The Bayesian is interested in this thing, the probability, how likely, or the hypothesis. Right? What's the probability of that hypothesis being true given the data? So the Bayesian wants to flip this around into what we call posterior beliefs. What is the probability that the hypothesis is true, and this could be either the null hypothesis or the alternative one, given that we observe a certain data set? Now, a frequentist statistician cannot do this because you don't have a probability on a hypothesis. It is either true or not. But the Bayesian can say my degree of belief that this hypothesis is true given the data is some amount. So the Bayesian can do these things. We have the probability that a certain hypothesis is true without taking data into account. And we update this after we see the data to a probability that our hypothesis is true given that we see a certain data set. Right? My probability that clairvoyance is true is 1%. I see BEM's work, now it's 5%, for example. Still low, right? Subjective, but increased. Now, how do we do this? A central concept in Bayesian statistics is that Bayes' theorem can be used to update this prior belief to posterior belief. And this is a formula. If you go back to my lecture on probability, where I actually explained these terms, right? The probability of A, the probability B, the conditional probability, the marginal probability. You can derive this yourself. If you want a fun exercise, try to do it. I'm not going to require it from you, but you could try to derive it yourself. But this formula is a way that you can basically flip this thing around to get the probability of hypothesis given the data. So what happens here? We have our posterior belief, the one thing we're interested in, equals our prior belief times evidence. And that's this thing here. We have the likelihood, and a weird thing here, the probability of the data given, not given any hypothesis, which is a weird thing, but you can calculate it by summing over all possible hypotheses. Doesn't matter. If you combine these things together, you basically get evidence. And we can do this for any hypothesis. So we can do it for the alternative hypothesis, but also for the null hypothesis. Basically, our posterior degree of belief, how much we believe now, equals our prior degree of belief times how much evidence is there in favor of this hypothesis, which we calculate from this likelihood itself. However, obtaining this marginal likelihood can be pretty hard. We have to sum of all possible hypotheses, basically. This might include hypotheses that we haven't defined. It can be tricky. Right? It's like a thing in this formula here, this part here, that is actually there. Something that is hard to do. Luckily, there's a trick that we can do to get rid of this annoying thing, this annoying marginal likelihood that we don't want to calculate. The idea is we simply take this and divide it by this. If you do that, this term is in both. That means it cancels out. We call this the posterior odds, the probability that the alternative hypothesis is true divided by the probability that no hypothesis is true. And we can do this really for more hypotheses as well. Right? So it actually would lead to times P, D, P, D. That's not very important. This thing drops out because it's the same thing. It becomes 1. Now I have something we call an odds ratio, rather than probability, but it's similar. An odds ratio means how many more times is one thing likely compared to another thing. So if this thing is, let's say, 1, it means that the alternative hypothesis and the null hypothesis are about the same, about equally likely. If this instead is like, let's say, 10, it means that the alternative hypothesis is 10 times more likely than the null hypothesis after we see the data. Now this posterior odds consists of 2 parts. The prior odds that quantify how much more you believe in one hypothesis compared to another before observing the data. Right, so for example, for my case of clairvoyance, it would be 0.9, 0.01 divided by 0.99. If I have a 1% belief in the alternative hypothesis and 99% belief in the null hypothesis. That's something you can fill in. That might be different for every person. The nice thing is that this second part here does not rely on something subjective anymore. This is not about a subjective degree of belief in the hypothesis. This is the likelihood. The likelihood according to the alternative hypothesis and likelihood according to the null hypothesis. The probability of finding a data set, but actually gets back in there. The ratio of these two likelihoods. The nice thing is that this thing is objective. It doesn't rely on this subjective degree of belief. And it tells me, basically, how much evidence is there in favor of one hypothesis compared to another one. How much more should I believe in one hypothesis after seeing the data? We call this the Bayes factor, or BF, like your best friend. And this Bayes factor is what the Bayesians use as alternative to the p-value. Right, because it's an objective measure that we can get that tells us something about how likely is one hypothesis compared to another, or how likely is the data in the one hypothesis compared to another. And we can use it, theoretically, to update our posterior odds if we want to. And I can do it. I can give you a Bayes factor based on my research. I say, my research shows a Bayes factor of 5. And you could, in principle, use that to update your belief. And not many people actually do that. Many people just report the Bayes factors in the paper, but that's how it's used. So the Bayes factor is a measure that is always positive and centered around 1. It's been proposed as a Bayesian alternative to the p-value, and it quantifies the evidence for the alternative and the null hypothesis. Basically, and this depends here on this subscript, we see 1, 0, which means we compare 1 alternative to 0, the null. It could also be 0, 1. Then we do the other way around. We compare the null to the alternative. And this is something we can do in Bayesian statistics, which is really cool. In this case, if it's higher than 1, let's say 3 or 10 or 30, you see it's more strong evidence for the alternative hypothesis, that there is a difference. The nice thing is, the closer it gets to 0, yeah, so this is 1 over 3, right? 1 over 10, right? So that's kind of symmetrical like that. The closer this is 10, yeah. The closer this gets to 0, the more evidence we have in favor of our null hypothesis. Now that is a very strong thing that we can do. We can get evidence in favor of the null hypothesis. Right, so for example, suppose that Ben reports a Bayes factor of 3 in support of precognition. But my prior beliefs are that precognition existing is 12 times less likely than precognition not existing. What should my posterior beliefs be if I use Bayes' theorem to rationally update my beliefs given this new information? Alright, so BF₁₀ equals 3. My prior beliefs, so my belief that precondition existing divided that is not existing is 1/12. So what should now my posterior beliefs be? We just multiply these things with 1/12 times 3 equals 1/4. Which means that now, after seeing the results from BEM, I still find it 4 times more likely that precondition does not exist compared to the precondition does exist. Right, but it went up from 12 times more likely. So first I thought it was 12 times more likely that doesn't exist. Now it's only 4 times more likely. And that's how I can use this Bayes factor. So the Bayes factor is a Bayesian alternative to the p-value with some extra benefits. It is more interpretable than p-value. The p-value is just a number under the null. It's with a large sample size, will always go very much to 0. You can't really interpret the p-value. You can't really say that p is 0.001 is very strong effect or not. That is completely dependent on the sample size. It's not interpretable like that. The Bayes factor has an interpretation, right? Bayes factor of 10 to 30 is strong evidence. And there's a strong interpretation like that. The Bayes factor quantifies evidence for both the null and alternative hypothesis, which is a nice thing. So maybe sometimes you're actually not interested in the alternative hypothesis, you're interested in the null hypothesis. Like for example, one of the groups in PL2132, they research if you can put the video on double speed, right? So maybe you are listening to me at double speed. Now, I should maybe speak slow. But let's say, okay, you try out normal speed, double speed in a sample. And maybe you try to see if people learn as much, right? And they recall as much from the lecture, if it's normal speed or double speed. The hypothesis you're interested in is seeing, okay, can I put a video in double speed while still retaining as much from the lecture as I would normally do if it's on normal speed? So you're actually interested in a null effect. You want to see that there's no difference between these two groups. Because if there's no difference between these two groups, right, that means that you can watch the video on double speed and retain the same knowledge, which saves you time. In that case, you might want to do Bayesian analysis, see if you can actually find support for this null, like this absence of a difference. Another thing, I don't want to talk about it too much, but the Bayes factor can be used in optional stopping designs. It allows you to do that because it quantifies evidence. And if you get more data, you use Bayes factor, Bayes rule again, basically to update your knowledge then. So because we use the Bayes factor to objectively update our knowledge as data comes in, we can actually look at it at any point in time. It's not tied to a certain sample size. It is a very nice thing to do. So you're collecting data, we could look at the Bayes factor, see, okay, Bayes factor is above 10, I stop. I have enough evidence and I stop, and that's perfectly allowed to do. And it doesn't lead to the same issues we have in frequency testing. However, unfortunately, there's some downsides. I mean, there's a reason why not everybody is Bayesian now. The alternative hypothesis has to be defined as a range. This is a really technical thing, and I'm not going to bother you with it too much. But in null hypothesis significant testing, as the name says it, we're actually only looking at the null hypothesis. The p-value is based from the null hypothesis. There is no effect. The effect is 0. It's mathematically pretty hard to say, okay, if it's 0, we calculate something, sure. But it's not 0. What is not 0? It's like difference of 2, 5, or 10. It's unclear. And a Bayesian cannot get around it. A Bayesian has to define what not 0 means. Which basically means that we have a 0. Right, the effect is 0, easy. H1. Right, so the effect is not 0. Right, so let's say beta equals 0. Beta is not 0. How do we define it then? Well, maybe like some distribution, like it can take some values around 0, but you have to calculate this and like define this, which is actually pretty complicated. and actually also in part subjective. Like I could have a different distribution there than you. That's a technical thing, and I don't want to bother with it too much, but this is actually a pretty complicated thing in Bayesian statistics, that you have to define these distributions. And JASP will give you some distributions, will do it for you, will choose very good distributions that you can choose. Some Bayesians will disagree with that because they'll say, oh no, this should have been subjective, you should have defined it yourself, but that's kind of hard to do. Base factors are also hard to obtain and sometimes have to be obtained through lengthy sampling procedures. And the math is actually pretty complicated behind getting these base factors, and sometimes it is just not possible. The only way you can do it is by a procedure that samples data over and over and over and over again using random draws. It's pretty weird. It works, but it is a little bit random. You might get some different exact results every time you run it, and it will take a long time. That's the main downside. Now, the stuff that's implemented in JASP is actually pretty fast. But definitely some of the more complicated Bayesian analysis might take definitely longer than your frequentist analysis. Well, and there's some more things to check to see if it actually went okay. And the base factor also very strongly correlates with the p-value. So it is not even that different. Like it allows you to get evidence for the null. But basically, if you get very strong evidence according to the base factor, you probably have significant effect. But they're not like, it's not always different. Like you might just get the same conclusion, whatever you use. All right, so as I said, JASP is designed as a Bayesian software. It's designed to do Bayesian analysis. And it was its main purpose. That was actually intended to be a Bayesian software, then decided to include frequency analysis. Basically as a Trojan horse. So yeah, sure, you do a stats course, you download JASP for free, it's nice, you can do all your ANOVA and all your t-tests, right, everything. But actually inside there are Bayesians hiding. And you might just be compelled to press the Bayesian button software. They also release all kinds of books and materials about this. There's a free online book, Bayesian Ticking for Toddlers, which you can read. I always have to read it for a while. I had to read it every night. To my 3-year-old at the time, he really loved it. It was a bit awkward because I'm actually a frequentist, but okay. It's nice, it's fun to read. And there's also another book that they wrote, Bayesian Inference from the Ground Up, which is free and online. And of course now also the JASP book is also available from Field. It's about frequency analysis, but it does have some points as well for Bayesian statistics. All right, so let's actually take a look at JASP. So this is JASP. This is the AI versus real data that I collected earlier in the course. Students saw photos that they choose or rate the certainty on if it's AI generated. We can do ANOVA, and now we can go to the Bayesian button. And actually all of these methods have Bayesian alternatives. Go Bayesian, put our dependent variable in. Then we have the type and the photo. And the input is the same. So we see a bit of different output though. See here, this is our prior. And what we see here is actually Bayesians do model comparison. Model with only the intercept, one with the main effect, with another main effect, with only the main effects both, and the interaction effect. Which of these models is the best? You see here that we use Bayes' theorem to get this posterior probability, saying that this model with the interaction effect is the most likely to be okay. That means that the interaction effect seems to be something we want to include. We can press effects here to get a table that's a bit more like that what we see before in ANOVA, where we just have the main effect for photo, main effect for type, interaction effect. And we see a Bayes factor for including this term. Right? Each of these quite strong, especially the type. Right? People were the photos, the 3 different photos. Type is if it's AI or real. People were pretty good actually in discovering which ones were real and AI. And the interaction, which we also saw earlier. And we can see here we can also get evidence for the null by switching these things around. Which in this case, actually there's no evidence for the null. There were actually effects in this data. Alright, that's it for this last video on Bayesian analysis.